discuss the idea that, well, space-time, in comparison or special relativity cases, seems pretty solid, and it's in that sense that we're going to question space-time, because if you compare the two, one theory, namely the relativity, is in some senses more physical than quantum mechanics. So if we're going to question either, why don't we question what seems to be the stronger theory? I just note that at this conference maybe it isn't considered to be the stronger theory, but we're just going to take that picture. But in a sense, relativity seems to be a mathematical encoding of a physical picture. I mean, we're basically starting with just a couple of postulates that seem fairly strong, whereas quantum mechanics, has a long history of reverse engineering results, and we finally come up with this theory that looks beautiful, but in some senses there are as many interpretations as there are physicists. So it's a bit tricky. So what we're going to do is say, well, look, physical arguments of special relativity are strong and transparent, but they miss quantum mechanics. So why is that? Well, okay, so here we have the two initial postulates of special relativity, equivalent physics in different inertial frames, and the constancy of the speed of light. They seem pretty direct and unequivocal, right? And yes, it's true that the theory you end up with has some peculiar features, and there are some paradoxes, but it seems pretty straightforward. When you start looking at it from the point of view of stepping outside the theory and saying, well, look, we have quantum mechanics, and it's conceptually a very different thing. It turns out that the culprit that in a sense allows classical special relativity to miss quantum mechanics is the idea of the smooth whirlwind. Right? Built into special relativity, we have this very classical picture that if we have a particle moving in space and time, the path is smooth, and you associate events with just positions in space-time. So, we can look at that and say, well, that clearly is going to be incompatible with quantum mechanics, in the sense that if we really do associate events with points on the world line, well, then we can get them arbitrarily close together. If we get them arbitrarily close together, we're going to violate the uncertainties. So the question is, can we amend special relativity directly to allow room for quantum mechanics? And the fairly obvious thing to do is to say, well, look, let's go back a bit, sort of in a sense pre-Newton, and say we're going to be in a discrete space, and we're going to build a clock. The clock is simply a tick periodically, so the number of events is countable. We're not going to run into this specific problem that the events are too close together. We wanted to probe high frequencies in order to be able to look on fine scales. It's going to be periodic, so instead of having a clock like a lot of macroscopic clocks that work on a decay principle, we want this thing to be periodic. And the clock mechanism we're actually not going to specify. Only that the events, only looking at the sequence of events generated by the clock. So the clock itself is digital. It just ticks regularly. So for the time being, we're going to suspend being physicists. We're just going to be applied mathematicians, and we're going to just build this clock. And we're going to make sure that it corresponds to relativity. So here we are. We have this sequence of events, right? And they're periodic. There's little circles on here, and we can think of, well, we have future codes. Okay, so here's C is equal to 1. We have the past codes. And so the event sequence, in actual fact, is a sequence of these space-time areas. Okay, so where the boundaries of the areas cross are the event. We can think of these as ticks of the clock. And we can can think of it as a chain of these spacetime areas. We're actually going to preserve orientation because we're going to look at these things and ask, how do these things change when we do a boost? So, so we're actually going to think of this. This is our, in a sense, two photons. It's simply that the areas in these chains don't change. They're independent. The area of these little rectangles. So, I'm not sure how we get to the next slide.
Well, controller with the buttons.
Sorry?
The button on the controller.
Oh.
No. The rack controller.
Yes. Okay, so event sequence and causal areas. So, if the event sequence obeys the Lorentz transformation when the areas are invariant, yes. Finite time between the events means that we almost always have a finite uncertainty time. So we can, in principle, fit this thing into this event sequence. We're not going to violate this because we have a delta t that's non-zero. We don't have to go to sort of singular ends. And we don't run afoul of this fact that if we really have a smooth world line, we're sort of up the creek in terms of quantum mechanics. So, we do have a problem though. Conventional relativity requires the reference frame of quarks of arbitrary precision. So how are we going to build these reference frames of quarks? Well, not too difficult. First of all, let's just see how we're going to interpolate. Think of an outside boundary of one of these clocks. So here's the right-hand boundary of one of these clocks. What we're going to do is this is a digital clock, so we're going to store the information digitally. So here there's going to be a right density that's going to say, okay, we've got one thing moving to the right. Yes, here's a 1. Nothing moving to the right here. Here's something moving to the right, but it has the opposite orientation. So instead of being 1, 0, it's going to be minus 1, 0. This guy on the left-hand side records this part of the boundary. Right? So all we're doing is, in actual fact, recording the boundary itself on these two component vectors, and we're preserving the orientation. Okay, so every time one of these guys changes, it's one of the ticks. Actually not one of the ticks, but it's one of these guys, either here or here or here or here. So that's our state change. So the state change variable is a characteristic function for the orientation of successive areas. So here's our set of states. If the and how do we go between these sets? So the first part of the chain is here, there, there, there. You can see the thing's periodic, and the way we go between states is what we can go through matrix multiplication of this guy here, which you've already seen. You already know this is a representation of the square root of minus 1. So since we can go through this, we can go through this sequence of states by multiplication by this thing, K keeps track of the number of ticks in our clock. Okay, so transition to continuous time. How do we do that? Well, we used this idea once to build a clock. We just build a higher frequency clock. So we say, okay, we're going to use the same idea. We're going to just increase the frequency. Same sort of thing. We have this sequence of change. And this is change. So here, okay, so we're not going to see this. Well, okay, all we do here is say, we're going to build a finer scale clock. And if we do that, if there are n ticks between these two ticks, then t to the n has got to be t. So we're looking for the nth root of this thing. And you can see that we're just taking the nth root of I, basically. When we do this, so when we take the nth root, we can look at the previous thing, which was the nth root, and then we can take the continuum limit. So we have this thing, and when we look at it, we say, well, look, this is the identity matrix. This thing looks like the square root of minus 1. this whole thing just looks like a complex number. Okay. And our plot agrees with the periodic plot that we started with, but now we've got actually an interpolation, because this guy can now be any real number. Okay. Let's just see what this thing looks like. So here's the original plot, right? It just has this. It has four states. We can see it's built into a three-dimensional space where t is up here, and the two states go around in this particle spiral. At double the frequency, we can see, oh well, look, this is beginning to look like a spiral. Here it is at 10 times the frequency. So we can see this whole thing is just building this spiral, which is the interpolant for the fact that our original clock started out with just a series of events. So, all right, so Minkowski's clock. So here we are. We've got this thing. It looks to us to be, it's written like this. It could just be a complex number, because t is just the square root of minus 1. In a sense, it's a representation of it. But we know that in relativity, we don't have absolute time. So we can't just have a single clock sitting there. We can't really represent time as a complex number, because it depends how fast you're moving. We couldn't get the twin paradox with this clock. But when we started this thing, we actually did build in a 2x2 matrix representation. And notice here, if we look in through the light cone coordinates, the states of moving right and moving left, moving right and moving left, they have different occupation times. And we can take care of this in order to take care of time. And noting that, well, here we want to increase the frequency or increase the duration on the right, decrease the duration on the left, and when we do, here's the infinitesimal version of it. And when we take the continuum limit, we get this. So here's what we just call Minkowski's clock. The only difference here is the even part really looks the same. The odd part has this multiplier. So this takes the place of t, which we thought of as a matrix version of the square root of minus 1. Notice this thing is in a sense a vector. It's a vector with negative norm, just as t squared with minus the identity. This thing squared is minus the identity, and this thing agrees with the two-photon clock, where we just had it ticking and we had no interpolation. It agrees with the dilated interface. Its square is minus 1, and this vector points in the direction of the proper time axis in the moving frame. So Minkowski's clock is quite like an ordinary clock, an ordinary analog clock, except it has to preserve two things. It has to preserve where you are on here, but it also has to preserve a direction. Right? Because in relativity, you need to know what the velocity is. So Minkowski's clock simply stores the time evolution and direction information needed by special relativity. Okay, 3D. 3D is actually straightforward. All you do is you embed this in a 3D space, and so your vector B actually has to be a vector. So here we'll use the Pauli matrices to represent the vectors. And when you do that, take the continuum limit. Here's what you get. And you see, just like you had before, except here, we see that the Dirac matrices come out, right, where the alpha and beta stand in commute because they represent directions. Okay, classical implications. This basically shows you where the odd signature of space-time comes from. Right? When we looked at the clock, we saw, we needed in the encoding, you always got, in a sense, vectors that had different, one had a negative norm, the other had a positive norm. It was how you built the clock in the first place that gave you the signature. Okay, so the clock encloses the direction of information. From an algebra perspective, you get this because T is actually a bivector representing the space-time area with invariant norm. Right? The thing that's invariant under a boost is the area in that little chain. It's because relative parts of base and invariant space-time areas, the space-time vectors have different square T's. So this is the origin of the familiar T goes to IT that takes Euclidean space to Minkowski space. Okay, so what is wrong with space-time? Well, the invariance of the causal areas gives rise to the odd signature of space-time. That's where it's coming from. The fact that the area of this little die doesn't change when you do a boost. So the continuum limit that gave rise to an arbitrary high-frequency clock shrinks the invariant area to zero. Right? When we do this thing, we're just saying build clocks of higher frequencies. When we build clocks of higher frequencies, we're shrinking down the area that actually controls the clock to zero. In practice, this means that the infinite precision reference clocks of relativity are of infinite mass. Now, I haven't actually shown that. We'll just see that in a minute, really. The frequency actually is controlled by the mass of the object. We think of this thing as a quantum. So conventional relativity, by invoking this thing at a differential level, forgets the origin of the relation is an invariant space-time area related to the mass of the clock in question, and so it's actually scale dependent. Okay, so by invoking this thing, as soon as we put this in differential form, we lost this aspect that it's an invariant area that determines how we measure time in the first place. So, from the perspective of the two-photon clock, it's okay to provide the precision of the frame clock is not used on such fine scales that it probes the clock mechanism of the observed object itself. Right? As long as in the end you're not probing on scales that are below the resolution of the reference frame clock, and that's fine. Now here, in conventional units, the inner scale of the clock is really the Compton wavelength. So this whole thing works for specifying particles being clocked at the Compton scale. Well, this seems to be at odds with quantum mechanics, right? Because we know that the characteristic length of quantum mechanics isn't actually the Compton scale; it's the de Broglie scale, and that's not, and that is velocity dependent. So what, if anything, does the de Broglie scale got to do with our clock? Well, what it has to do with the clock is simply this. Here's one of our clocks ticking away. Here's one moving with a speed v. And if we ask for the situation where in the moving clock we've lost one tick, we see, oh, well, the distance measure for that is h over mv. Small v. So it's just the de Broglie wavelength. So there will be a point in space and time where the moving clock will resynchronize. The stationary clock having lost a single beat. That's at this characteristic length. And note here the disappearance of the frequency from the rest matter. This does not involve C. So here the de Broglie wavelength is geometric in origin. It arises from the beat frequency of a slightly different frequencies of the zeta vega. In order to create a clock that moves with speed v, we had to take those, what were initially squares, make them into rectangles, which gave you two slightly different frequencies on the left and right line. Okay, so now we have to ask, well, what really happens between the ticks of the clock? We built a clock that does this, and we're saying, we don't know what happens between them, really. We've outlined a causal area where the clock mechanism must take place. So, what happens between the ticks? Well, okay. So this clock ticks at the audible events. The causal areas bound the unknown clock machinery. But in terms of the paths, the number of paths is indefinite. The way to see this is just to think of this expansion. Right? Here's the thing that drives the clock. Right? rotation, this encoding of -1, notice you can write this out in a Maclaurin series in terms of itself. This is the square root of -1 referring to itself, and with each of these is associated a path. So if we looked in here, we could write this in terms of miniature paths which look like the original. So what happens if the audible ticks are silent? Well, you know, Minkowski's clock ticks at the audible events with an indefinite number that are silent between ticks. If we cannot hear the ticks, then one possibility is to say, okay, the ones we can't hear, that all the clock does is simply expand, and it moves over the area that we cannot check. Right? This is actually what happens with the Breuer waveform. Right? In a sense, what you can't see won't hurt you. Well, maybe what you can't see is incorporated into the whole sequence. So what does the mathematics say? Well, the Tig matrix for stochastic clock satisfies the Dirac equation. This is the chessboard model. It's a very popular model for looking at the Dirac propagator in 1 + 1 dimensions. But then you ask, well, how can this be, given that Minkowski's clock is classical? We don't have interpretive problems. We know exactly what it's doing. We know exactly what it's counting. And we know why it's being counted. Well, okay, what happens with the chessboard model? You're looking at infinitesimal displacements in time between the audible ticks. So this picks up this thing here. So the ones you can't see, and you put in terms of a stochastic model, you find, oh, well, the whole thing obeys the Dirac equation. So the infinitesimal steps of the PDE take place between the regular collapse to audible ticks. To a quantum mechanic, Minkowski's clock is a manifestation of the quantum Zeno effect. If we really do hear a tick, 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 tick along there, it suppresses all quantum mechanics because you're observing. So it just does what you expect it to do for the classical way. If you don't do that, and you really can't detect any of these things in here, then it just becomes a clock with a lower frequency with the same peculiar, possibly quantum mechanical behavior between the ticks. So, you know, to a classical mechanic that tackles the problem between the ticks, there's a form of wave propagation that happens between the ticks of the clock. The thing that drives the thing in the area where you can't see it, or can't hear it in this case, is actually wave propagation. So this is conventionally hidden by starting the continuum with smooth whirl lines. You start with smooth whirl lines, you don't see anything. Okay, so quantum mechanics is a relativistic fact. So let's just step back and look at Newtonian mechanics versus relativity. So in Newtonian mechanics, you know, we use the absolute time as a theory that works spectacularly well. At least it did until we decided that it wasn't quite good enough. And then with Einstein, we said, oh, well, really, there's an extension to Newtonian mechanics that brings in this rest mass term, the energy, and these higher order terms. So this kinetic energy in here is actually special in the sense that it's part of this expansion that doesn't see the constant c. So it doesn't warn us that this absolute time is actually an approximation to the relativity in which there is no absolute time, there is time dilation. So this is sort of how historically things were put together and how the subject is itself taught. Of course, the reality is quite different. The reality is this is more like what we've got, right? And it's a bit of an accident that you can carve out this piece here and have a nice complete Newtonian mechanics with absolute time. Okay? So that's how it looks in classical mechanics versus special relativity. When we get to quantum mechanics, we have the same sort of thing. Schrodinger's equation came before the Dirac equation, and And we were more familiar with this than we were with this. So Schrödinger's equation said, okay, let's work around non-relativistic quantum mechanics, and we'll come up with these prescriptions which give us the usual non-relativistic quantum mechanics. And Dirac came along and said, well, look, we've got all this stuff to do. Right? So here's the relativistic extension where we build this in and we get the Dirac equation. That's the appearance. The reality, of course, is simply this. That this is where we start. And so the reality, in a sense, is the Dirac equation. The appearance is the inheritance from Newtonian mechanics with absolute time and the usual quantization. So the interesting thing about this progression is that wave propagation depends on c at the Compton scale, but it generates a beat frequency at the Broglie scale, which is what we see and detect, in anything to do with chemistry. Right? Just as initially in classical mechanics, we saw this thing and said, this is where we live. We've got absolute time. We've got a kinetic energy term that looks like this, and we built a theory around that. So with Schrödinger's equation, we did the same thing here. We said, oh, it really doesn't make any difference whether it's absolute time or whether it's relativistic time for our purposes. But the thing that we missed in that is that just as we can't see what the constant c with this term, when we look at Schrödinger's equation and non-relativistic equations, we don't know where the wave propagation comes from. We have to fudge it in there by doing a formal analytic continuation. P goes to minus I h bar Bragg. So low-speed classical physics does not see the relative terms because they change them along classical scale, but does see the remnants of power dependent upon the time. So this is where I think you sort of learn something there. So conclusions. The continuum limit in space-time is an infinite mass approximation. If we go back to the Dirac equation, we see, oh well, how do we get this thing? How do we get to take the two-photon clock and give it infinite precision? We effectively, from the point of view of the Dirac equation, we sent mass to infinity. So the whole space-time frame of relativity is an infinite mass approximation. And in the teaching of it, of course, well, what do? You set up kinematics, you set up the Lorentz transformation, and then you bring mass in through the dynamics. And it really is a two-stage process, because to get to the space-time frame in the first place from the clock, you actually have to take an infinite mass taken to the continuum limit. And so this is quantum mechanics. In quantum mechanics, the wave propagation has a threshold frequency, i.e. the Compton frequency, that may be decreased by geometry. This was this funny de Broglie effect, where if you look at a stationary clock and you look at a moving clock, you ask the question, okay, when is the moving clock going to lose a single tick? When you do that, you see, well, okay, that gives you the de Broglie scale, and also shows you why old quantum theory works so well for things like simple like the hydrogen atom. Okay, so both the T going to IT of Minkowski space and the T going to IT of Schrödinger are in a sense remnants of the Lorentz invariant space-time area. And it's because you're actually, in a sense, going to a linear measure from an area measure that this square root of -1 comes in. The other thing that is sort of interesting is that the path-dependent phase of quantum mechanics then is in actual fact a remnant of the path-dependent proper time of special relativity. So you see, in a sense, that instead of the Dirac equation being a marriage of special relativity and quantum mechanics, that actually both children of some prior thing that sets up the special relativity and sets up the quantum mechanics. We just don't see it because we start in the continuum. As soon as you start in the continuum, the differential operators mean different things. The differential operators for relativity are, in a sense, based on behavior over large scales. In quantum mechanics, they're based on behavior on lower scales. They're different approximations. They mean different things. So that's why I think you don't really see that if you start to continue. Okay. Well, thanks for listening.
Very good job.
You made 99 steps of 100 to answer the question why the speed of light is finite. Or you have done 100. Can you answer
No, you have to hear that last step. I mean, it is finite, and because it's finite, you can get all this stuff. Right?
The answer is here in your.
You're not going to tell me?
Okay.
Okay. Well,
You are a mathematician?
not really.
So anyway, the matrix T that you have shown us, this is a generator of the symplectic group. And if you look at the cohomology group of that, then you get the group of two elements, C2. And this explains why you get this covering that you have on going up. And if you look at the projective space, then you can make the reunion of these large scales and the small scales. So this fits together.
Well, I'd love to see that actually. So
Could you write that down and send it to Garnet? Could you write what you said and email it to Garnet?
Yeah, I can.
For his use.
But it was in my talk yesterday.
Yeah, but see, I'm not sure he was there.
I was there, but I moved rather slowly, absorbing these things. So I would have to see it.
So the key is algebraic topology to look at the cohomology group of this setting of the symplectic group.
Okay.
Other questions?
You said that the Newtonian absolute time is an approximation, but approximation of what? Maybe the relation is different. Maybe it's similar to the relation between physical metric and the background metric, so-called biometric gravity theories.
Okay, I guess from my perspective, all of that stuff that deals with metrics and you know the formulation of general relativity, it all starts at the differential level, and it all starts really by forgetting the fact that if we're going to build any sort of a clock, we have to build it out of matter. And if we build it out of matter, then in order to get a precise clock, it has to get bigger and bigger and bigger in terms of mass. So that whole paradigm is based in a sense from the quantum mechanical perspective of saying, let's make the approximation right now that there's such a thing as an infinite mass reference frame that can be arbitrarily precise.
So approximation of what? Newtonian absolute time is approximation of what?
Okay, so with Newtonian absolute time, you could have got away with that approximation by saying, let's assume there's a clock somewhere, a Big Ben out there, make it a bit more massive, and let every point in space sample that clock, because simultaneity doesn't care about the relative velocity. So it would have been quite benign in that context to say, you know, we have arbitrary precision. But it's not benign as soon as you have something to base special relativity, because time, duration, is path dependent. And in the usual picture, you would have to say something like, well, space-time informs the particle how old it is. It doesn't actually specify how it does that, but you just assume somehow it can. The particle moving in space-time is informed by space-time how old it is. This thing here says, okay, well look, just build the clock. It's a very special clock in the sense that it's built on light code. But as soon as you do that, you see, oh, in order to do that, what you're essentially doing to get infinite precision is you're going to infinite mass, which then all of these space-time frames that we use in relativity, you already made the approximation that you have an infinite mass reference frame. And when you go to the differential forms of these things, you've already missed the bit that could bring in quantum mechanics.
One final question.
To your question, what is wrong about space-time, a very short answer. Wrongness about space-time that it is completely unnecessary. It makes life complicated and causes problems and open questions in physics which otherwise would not exist. The alternative to this space-time, following Einstein, is the Lorentzian relativity, and I will show tomorrow it is so simple. Our world is so simple. If we follow Lorentz, we get the same answers, analytically the same answers like with Einstein, but it is much easier to understand this with our brain. That would be my answer to this question.
Okay, my answer took a lot longer, I have to say, but I think I would agree with you that the end stage is probably similar.
One piece of business before you go to coffee, but let's thank Garret.